Yep, it should show up in your calendar.
Okay, thanks. I have to leave a little bit early. I have
Okay.
a meeting with my advisor, so just want to make
Yep.
sure I'll go back and watch that.
Yeah, I think I've been recording about every one, so they should all be back there for review along the way. Here's where we ended up last time, where we were looking at a store. One store growing at 50 stores per year. So every year following year 0, we have 50 more stores. The first year, the result of the first year, both stores have the same number, 150 after the end of 1 year. Looks great. Second, or year, store A, company A, says, okay, every year we're going to increase by 50 stores. Well, that's not a bad growth for in a plan. Every year you just have 50 more, find 50 new places each year, and you're growing by 50 each year. There's my growth. It's a linear growth. Every year I know that I'm going to have 50 more stores. After 1 year, I have 50 more stores. So my slope of a linear function is a slope of 50. Company B, though, they decide to be a little more aggressive. They're not just going to grow by 50 stores. They're going to grow by 50% each year. And so first year, 100 stores because it's our 0th year. Second year, 50% new stores, 150. Now the third year, we're growing a little faster. Half of 150 is 75 new stores. So this represents not a linear growth, but an exponential growth. 1.5 to the number of years gives me 50% growth every year. And that is a lot harder to do because each year you have more stores to plan. But your investors are going to love you because hopefully you're selling just as much in all your stores, and so you're growing in income exponentially, percentage every year. Someone comes along and wants to invest $1,000 in your company, they know that every year their investment is going to grow by half of what they already have. So the second year they'll have $1,500, and the year after that, half of $1,500 is $7,500. So they'll be 225 the second year. Their investment is growing a lot faster. Now these guys, they invest $1,000 into the store or into the company. Second year they're going to have $1,500 more. Third year, $2,000 more. A steady growth, and over time it gets easier, but my investment is not growing nearly as fast. But it is a safe investment because it's easy. Once you have 250 stores, it's easier to have 50 more. If you, again, you're assuming you're getting income from all your stores. This is a safe investment, but it grows very slowly. So the important word here is the investment or return rate. My rate of increase here is 50%. This here, while the rate is initially 50% improvement, my rate is actually less percentage increase every year. Although it looks like, oh yeah, we're growing 50 stores each year, the actual rate percentage of increase is less. So my investment is growing, but not as fast, not by the same percentage each year. So that's why this exponential function is a big deal when we're talking about investment. Also, when we owe somebody some money, remember, if you owe someone money at a high interest rate, you owe them more over time if you're not paying your bills back. So not only do you want to invest, also remember people are getting more money out of you if you owe them money at a very high rate, 50% rate. So here's the two curves of those two stores. Store B, growing 50% each year. After the first couple of years, actually the first year, they look good. Immediately after the second year, we see store B is growing faster. And man, after 10 years, store B is way up there in value, where store A is increasing, but not nearly as high. Another real world example here is that population problem that we started out with this chapter, that we are growing at a rate of 1.2%. Think to yourself, if I'm growing at a rate of 1.2%, I have my initial population of 1.25 multiplied by, well, every year it increases, its population plus a percentage. 1.2% is equal to 0.012. Every year I'm increasing by that much, and so therefore you get this formula where T is in years. My population increasing by 12% each year becomes this equation. My population after so many years T will be exponentially increasing. And from this, we realize that when T is about 18, that means 18 years from now, that's 2031, I just put in 18 for T, and I will figure out what number I have for my population. Now remember, this assumption is, well, today's population of China, if they have zero growth, they'll have that same number in 2031. But if they are still growing at a small rate, 0.6%, that's 0.6% growth, their population growing much slower. Now, you could get into the whole politics of how they're doing that, forcing people to only have one child. And if they have more than one child, they have to hide that child or give it away, or they'll have abortion in China. But they are worried about the population growth, so they're willing to take drastic measures because they see problems with overpopulation. Now, as we start dealing with the exponential function, remember the standard form is f of x is in some standard form a times b to the x power. That's the standard form of our exponential function. Well, we know when x is 0, b to the 0 is going to be 1, so I'm going to get the value of a when I have x as my input. Remember, that's x, and then this is f of x in my parentheses. I know whenever I have a 0, whatever I get when I feed a 0 into f of x, my a value is now the model. So if I have a data point given a 0, I get some value, I know that my model for my function is, I know a value for a. And all I need is 2 points on the curve, 2 equations with 2 unknowns, a and b. All I need is 2 equations, and I can figure out what both a and b are. So 2 equations and 2 unknowns allows me to find a and b. Well, let's do that in a few examples here. They give you a word problem, those scary word problems, but don't panic. Just figure out, all we're looking for is a and b. When we know that our function is in some form of a times b to the x power, we know that and have been told that we have an exponential. Okay, so let's see if we can figure out what a and b are. 80 deer at the start. Well, 80 deer at the start at time 0, well, we know that at time 0 we have a value of 80. Therefore, a equals 80. We already know a from that statement right there. We know that 2012, Okay, now it's a little tougher. By 2012, we had grown to this. So I know that at some point, f of x is equal to 180. But what was my input? Let's see here. Well, remember x represents, in this particular problem, the number of years t. Well, 2006 is when I started. 2012, that is 6 years later. Therefore, t is 6. Or in our equation, we're looking at that's the number of years. So we know that 80 times b to the 6th power equals 180 deer. And don't be confused, make sure that that's clearly letter B. Well, what do I need to do? I know what A is, 80. I have to figure out what B is. Well, it's not really that hard. All I have to do is isolate B here. Divide by 80, and I'll make sure I get the right problem going here. Make sure I don't give you the bad values here. I divide by 80 and I get 6, so 180 equals b to the 6. Let's see, 80 b to 6 equals 180. And oh, we'll even just put it in a fraction. We won't even calculate the number. I know that b to the 6 equals 18 over 8. Divide by 10 real quick. Divide by 2 equals 9 over 4. b to the 6 equals 9 over 4. Well, all I do is take the 6th root of 9/4, or b equals 6th root of 9/4, and all they do in the book is plug that into their calculator. I get 1.447. Or sorry, 1.1447. So now I know A and B. So now I can write the exponential function n of t is equal to my A, 80, times B, 1.1447. I'll put in parentheses to make it clear. 1447 to the t power, where t is the number of years since 2006. T equals years since 2006. There's my solution to the n of t. Oh, and while I'm going over this, for your homework, for credit, make sure I save attendance here. For credit for your homework, your worksheet 4.2, all you need to do is take notes during this lecture and send me a picture of your notes. Worksheet 2 is also available there, and all you need to do for worksheet 2 is either mark it up electronically or have a hard copy of it. Boy, Google was really slow this morning. And just upload that to me. Here it comes, here it comes. All you need to do here for homework 4.2 is work through that worksheet, which I've given you a copy of here. And all you got to do is send me either the electronic form or the just your notes as you read through this and solve it. That's just a PDF from the worksheet. So you can just edit that. And I found Internet Explorer works really well. I can just mark it up. And if you'd like to rather just write your answer by hand on a note paper and then just take a picture of it and send it to me, upload it with your homework. That will count as completing this. And we'll start on this today. Okay, we're back to the exponential function. Another problem here. This time we've only been given 2 points and we're not given the point at 0. That would be the easy one. 0, I know, feeds me a. Well, let's see. This shouldn't be that hard. Let's see here. We know the function is in the solution. F of x equals a b to the x. Well, if I feed a -2 in there, ab to the -2, what do I get? I get 6. And I also have ab to the second power gives me 1. All I have to do is solve for a and substitute it in the other formula. 2 equations and 2 unknowns. And so let's go ahead and do that. Practicing, basically cranking through the solution just by feeding it my 2 values. Okay, so 6 equals ab to the -2nd. Well, we could solve this for a. We get a equals 6 over b to the -2nd. Oops. Or a equals 6b squared. And remember, b to the -2nd is 1 over b to the -2nd is the same as 6b squared. Well, feed that into here, knowing what the value of a is. Well, I have 6b squared times b squared equals 1. b to the 4th equals 1 over 6. b to the 4th, divide by 6. And I get b equals 1/6 to the 1/4 power, or the 4th root of 1/6, or 1 over root 4 of 6, or a value of 0.6389. Now, knowing what b is, I can feed it back into either of these equations, and they feed it into this one, and I can solve for a. So I take this b here, feed it into this equation, and I get a equals 6b squared equals 2.4492. And I ran out of room there. 2 equations, 2 unknowns. A divided by b to the -2nd, a equals 6b squared. Substitute into this one. I solve then for b, and then figure out what a is. 2 equations, 2 unknowns. I'll leave this one. Let's look at the graph and see how we can solve it just using the graph. Given my graph down below here, they have given me a nice value where I have x of 0. I know that I have value 0, 3. And let's see if it crosses the graph nicely at other points. Here's one good crossing point. Here's another good crossing point. I can take either of these. This is 1, 6. This is 2, 12. I actually have 3 points, and I only need 2 of them because I know f of x has the form a b to the x. Well, I can easily solve for a. This is the easiest one because when x is 0, I know that a is 3. So I know a b to the 0th power equals a, and I know the value is 3. So I know that one. So now I know the function is 3b to the x. Now I have to figure out what b is. Well, let's plug it in here. 3 times b to the 1st power, what do I get? Equals 6. x1, I get an output of 6. b equals 2. Just for fun, let's see if I get this. If I get the same answer for b here, I get, substituting this one, I'll put it over here. I say 3b squared equals, see there's the 2, b squared equals 12. Divide by 3, b squared equals 4. Now look at that, I get the same value for b. Substituting in 2 different places, basically because I have 3 points, this point gave me a solution for b, this point was just a check. And yes, I got the same value for b, just to check my answer. I could have gone further out this way, but there is no good integer value. I could guess that at -1 I get, looks like about 1/2, or actually, no, that would be 1.5. Oh no, let's not take guesses. Let's find the points that are crossing fairly clearly right at integer values. Then I'm more sure about my answer. So remember, I have to have 2 points. This is the easiest point to solve for a. Of the y-axis gives me a. When I have my function in the form f of x equals a b to the x, the standard exponential form. Always think that's the form of the function I'm looking for when I'm working with exponential functions. And what scientists do will say, they'll look at a problem and say, hey, we think the solution is an exponential. We think this models an exponential function. And if it did, let's see what a and b might be, and let's see if we can figure out an a and b that fits the data. So they'll have data following some line, and they'll speculate, they'll make a theory that maybe it is an exponential function. Let's find what a and b are if it were, and then they'll say, okay, the data is that, our model follows very closely the data, therefore we think we can predict, at least locally, what's happening with our physical problem, like a virus outbreak, or the population of my deer in the forest. We know, though, that over time the population is not going to go up forever. The poor deer will run out of room. And even before they run out of room, they'll run out of food because they need so much food and area. So we know over long term, when we model some real function, that it's not going to go up to infinity. It will go up, and then, oh, there'll be some other factor that keeps our function in real life from going on forever. And we call that the inflection point, or the log, I forget the name they give to the function. But anyway, in real life, our functions don't go forever. There's some other thing that stops it in real life. I'll call this real life, like population, or even the virus. There's not going to be an infinite number of people infected because there's not that many people in the world. The limit on however many get the infection is limited to the total population. So there's something that happens over a long period of time. But what happens right here, this is where we study the data and try to predict when it's going to stop infecting, or the deer will stop growing and then we'll have to do something. The disaster is, say, that deer population or human population, something horrible happens causing this. And we don't want that to happen. So we want, or a lot of suffering happens right here when we start to have a lot more problems. We try to keep that from happening. Thus the wearing of the mask, or the feed the deer, or control the population of the deer so you don't have the sudden collapse in the population. It's a horrible thing to happen. Okay, here's another graph. We're given, basically right away you should see, oh, I know what A is. We know A is square root of 2. Right away. They tell us that, even though it looks like 1.5. Do we know anything else about this graph? Well, let's look. We've got a good crossing point there. Close there. Looks like our only, well, and that's close. This looks like our best crossing point. So we know that f of 2 gives us 3. Well, we know what A is. They told us. And we know the form is a b to the x. And x of 2, or f of 2 gives us 3. We can say square root of 2 times b to the second power gives us a 3. Well, then we can solve for b. B squared equals 3 over square root of 2, or b equals square root of 3 over square root of 2, or square root of 3 over square root of fourth root of 2. Square root of the square root of 2. That's a 4 there. And plug that into our calculator and we would get a number. I'm going to skip the part about using your graphical calculator. Easy enough to plug your numbers in and figure out the square root. Now back to our most practical use. It's worth spending time on this just because this is what's going to happen to you when we're doing some investment or paying our mortgage. Let's think about this. Don't run away from this. This isn't that scary. Let's just think about this. This is some number, and I'm taking it to some exponent. I'm just throwing a few extra variables in there, but it still is just an exponential function. But it means a lot more as we look at this and get a good understanding, because this is something that will come up in business and finances. Let's see what what P, R, and N are. We're talking about compound interest, and we're talking about a nominal rate R for our interest, either something we're earning or on a mortgage we're going to owe. And let's see here. Time T, and that's in years typically. The principal, that means how much we're borrowing or taking out for the loan. I'll call that my loan amount. My annual percentage rate. And how many times I compound in year N. Compounding periods. That means monthly, my period number is 12. Daily, then N is 365. So N is how many times over a year I recalculate my interest. Keep track of that curve. So far, we've just been looking at the curve after 1, 2, 3 years and figuring out the function based on years. But there's a way to calculate, well, what is your investment worth today? We can figure out if we're daily compounding the interest. That's what this formula is about. So don't be afraid, don't be scared by it. It's just that same exponential function with some variables that mean different things, but eventually giving us the same form, a, b to some power. Instead of x, we're getting nt, and b is 1 plus my rate divided by of how many times I'm compounding my interest. But it's still an exponential function that we understand now. So after 1 year, as I calculate my investment, what we learn about here is we earn a tiny bit more if we're compounding daily. Tiny advantage. My investment over 1 year, if I'm compounding it daily, I get $5 more in my investment than if I just wait to the end of the year and do the calculation. And so the banks will say, oh, your interest is compounded daily, wonderful thing, come to us. Well, you get $5 more out of $1,100 or $1,000 investment earning 10%. So compounding daily, they spend more time on their computers and probably charge you more service fees because they're doing this compounding daily. Hopefully that's worth more than to the bank than the $5 extra you earn in your interest. They get you as a customer telling you, oh, we're compounding daily, you get better investment, when it really isn't a huge advantage. But there is some advantage when they calculate it daily. So they use that formula, compound it daily, and then you get your interest. I'm going to show you by showing you, I've done this in GeoGebra, my favorite calculator online. I'm going to bring this over here and show you this formula. I've programmed it into GeoGebra. There's my function using that R percentage rate, my initial investment, and my amount of compounding, how many periods. As I have this one, this is the daily compounded with an n value increasing. As n gets to 10, I'm almost matching the compounding continuously, which we're going to be looking at in a minute. There's just a slight advantage by compounding. Once I compound it more than about 5 times per year, I'm close to as though I were compounding continuously. So there's slight advantage to those two, to the compounding daily. But once you're compounding it monthly, you're about as good. So back to our little practice here. Oh, here's another problem. I have a value at I'm hoping to achieve a certain value after so many years. What do I need to put in for my principal if I want that much? Well, that's just simply plugging in the formula, putting in our known values. Let's take a look at that solution. Compounded interest, we're seeking a goal of so much money in our bank account by the end of so many years. Okay, so let's plug in our numbers into our formula. We know our formula is going to look like this. The investment after so much time, T in years, is equal to our principal investment times 1 plus my rate divided by the number of times I'm compounding it times NT. Number of times the number of years. Well, what am I looking for? I'm looking for 40,000 to be the final value over 18 years. So 40,000 is my P. 18 years is T. And my interest rate is 6%, so that would be R. And 6% is 0.06. And one more number to figure out is what N is. Well, semi-annually means N equals 2. Well, I have all my numbers except for A. No, I have all my numbers except for P. So let's plug them in there. I get 40,000 equals P times 1 plus 0.06 over 2 divided by, or to the power of 2 times 18. Well, I calculate this out and divide by it, and I get a number 13801 equals P. Just by calculating this, and 40,000 divided by that gives me
Why
P.
did you put 40,000 if we're trying to calculate?
Because we want the account to grow to that.
Oh, okay, I see.
And so that becomes our A. We want our final value to be 40,000. So all you have here, just like a lot of math, it looks scary here, but as we think through our problem, we figure out they're giving us everything except P, which we need to solve for. So it just becomes a puzzle. The hard part of the puzzle often is reading through this problem to see what numbers are they given to us. I know here's my formula. What are my values of R, N, and T? 18 years, T. 40,000 is what I want it to grow to. Plugging everything in, I realize the only thing I don't know is P, and I just multiply this out, or actually add these, take it to this power, to the 36 power, and then divide that over 40,000, and I get this as my principal that I need to invest. What does she need to invest now? Now, the more realistic solution, or the more realistic problem, they've actually given you a simplistic problem of, I'm going to invest one amount right now, and I know that after 18 years I'll have this amount. Well, what are we assuming? Well, we're assuming that we can believe we're going to earn 6%. That's a reasonable assumption. But Lily more likely has $5,000 to invest now and needs to keep adding some each year to help it to grow. That's more like your problem. You want $1 million. Actually, that's a small amount to think of. When you retire, think about your 401k. By the time you retire, you're going to need to just live at a reasonable rate after you retire, not earning any more money. You're going to need $1 million in your 401k, at least, to live in a mobile home park somewhere. Plan it for your life. You're going to want your 401k probably to grow to about 3 million or 4 million with dealing with interest rates. So your goal in life is you want and let's see, your career, you'll start working at around 20, say you get a good job starting about 20 years old, and by the time you're 65, you're going to retire. So that's, let's just say 45 years, you want your 401k to grow to at least, I'd say, in 45 years, 4 million is still going to be a fairly modest retirement fund to allow you to live in a mobile home with decent food. So you need to have some investment, a certain amount that you want to put away and add to it every year, so your final interest or your final amount for your 401k will be around that. Most people don't even think about this. They think, oh, the government's going to give me my Social Security. I have been planning all my life because I was told back in high school that Social Security would be bankrupt by the time I retire. It's maybe not looking as bad, looking like about 10 years. I'm hoping there'll be something, but I have not been planning for that. I have been putting away money in my 401k, and it is growing fairly well. Most of the time it has grown about 6%. This year has been amazing. There have been some investments that have grown at 80% in this year, but that's not normal at all. Most of the time it's been growing at 6 to 12%. Even 12% is impressive. And that's all about planning your life around this function. Principal, or your final investment, is based on an exponential, where your rate of growth is a positive rate of growth. And most of the time, investments need to be greater than 0%. If you don't have investments growing, at least you're not losing it. In recessions, that rate has gone less, and you have lost investments, and that's the scary part. We don't know what might happen to that. But the positive thing about no matter who is president, that the rates are generally still positive. Now comes one last thing we deal with exponential functions. We're talking about this special variable called E. And here's one way to look at it is, I have an investment. If I calculate my rate of return, or my final investment value, once a year, I get a decent increase if I'm 100% interest, which is amazing, doubling every year. Huge amount of investments. Even if I put $1 in the first year, after 10 years, my investment is going to be worth 1 times 2 to the 10th, because my interest rate is 100%. So my value of my investment is my initial investment plus 100% more. That's 100% is 1.00 divided by 1 year taken to however many years. So 2 to the nth, to the n number of years, is my final investment. So pretty nice if it's 100% each year. Well, if I start calculating my investment daily for that first year, here's the daily compounding. Remember how I said if you compounded more regular than wait till the end of the year, I get a slightly better investment. Well, here it's quite a bit better, almost 71 cents more. Pretty good. But see how once I'm gone past daily, it's not increasing by all that much. 718, 7182, 718282. As I compound it more and more, it's not increasing all that much. But because I want to see what would be the limit if I compounded it as much as possible, 1 plus 1 over almost infinity to the almost infinity power. What does that give me? Well, the limit is a very special number called E, Euler's number. As 1 gets larger and larger, basically going as n approaches infinity, what do I get? This very special number, 2.718282, and it's some of those numbers that the geeks might actually memorize out, 50 decimal points. It's pronounced Euler's number E. Don't worry about the calculus behind all of that. Basically, when we use E when we're compounding continuously. See, as We compound it many, many times every millisecond. We call that compounded continuously, continuous compounding. Then one investment invested at 100% after 1 year gives us Euler's number E. And E is such an important number, it's actually in your calculator. All you need to worry about is E has made my compounding for continuous growth a simpler formula. I don't have to worry about 1 plus r over n to the power nt anymore. As I compound it continuously, n approaches infinity. As n approaches infinity, my compounded continuously investment, I simply take my initial value times e to the power of my interest rate times the number of years. And now I have a simpler formula than initial value times this more complex. All I have to say is what's the rate, compounding continuously. I'll know what my investment will be worth after so many years. And we can tell the bank, don't compound it daily. I want you to compound it continuously using this formula, and I know I will have the best return on my investment. Continuous compounding. So now my formula for continuous growth is this function. I've simplified it. I can always go back to this thinking, oh yeah, I'm compounding it. I'm using this exponential function. As I compound it more and more times per year, I get this formula. Compounding infinite times per year means continued compounding. There's my formula for my investing, where A is usually replaced by P, my principal investment. Nice thing of, well, one disadvantage of this, when they charge you interest for your mortgage, for your loan, compounded continuously, this is also the formula for how much you owe when you've taken out this loan. So it may be your investment, it also may be your loan, aka your mortgage. Most people, that's the only time you think about this formula, when you are going to buy a house and you're calculating your mortgage. This will be the ultimate amount that you pay once you own your house. And typically T is 30 years. You want to be done and have paid for the house. They'll tell you in your mortgage estimate, here's how much you're going to be paying us by the end of 30 years. Thank you very much. We can take that money and do lots of things with it as bankers. So that is the fundamentals of exponential function. Comes back in real life. One last problem, and then we'll go to the next function, logarithms. So what we're looking at here is we have investing $1,000. We're earning 10% a year, compounded continuously. What is the account? How much it was in the account at the end of 1 year? So we know our initial principal, P, interest rate, R, equals 0.10. Compounded continuously, that means we know our investment is principal e to the RT, right? Check my formula. Yep. Well, plug in my values, and what do we get? And I have E on my calculator if I want to do that. And the solution I get is E to the 0.1, and T is how many years? 1 year times 1. So E, or the principal, e to the 0.1 equals 1105.17. I can expect that if this will indeed be my, well, here they're doing a nominal 10%. So the nominal value would be this. One more problem, and we'll go on. 12% interest. There's my R, 0.12. T equals 30. Principal, 100,000. P equals 100,000. Plug it in. E to the 0.12 times 30 times 100,000. Plug that into your calculator, and I don't have, well, let's see, I don't have my calculator right here. Just plug that in and you get a value. This one here, I'm decaying. What does that mean? Well, that means my rate is a negative. When I'm decaying, that means this is a negative percent based on decay. So R is negative 0.173. That's the key there. Decay. Otherwise, there's my initial amount, P equals 100 milligrams. And it's per day, so T is 3. And so I get a value of 100 times E to the negative 0.173 times 3. And I plug it into my calculator and I get 59.5115. That's how much radon 222 will have decayed to if we have properly predicted our rate of decay. And therefore, if I find this much radon in a sample that I know started at 100 milligrams, I'll know that my sample is 3 days old. But I'm making the assumption that it had pure, undecayed radon 222 3 days ago. I have to make that assumption to predict or to calculate the actual age. And this is actually how they calculate ages of rocks based on decay of various radioactive compounds, making assumptions of what it must have started with. Okay, enough of that. Going on now to the inverse function having to do with exponents. So our logarithmic functions now in a new chapter. This is the textbook. We'll mark it up as we read through this and then work out some problems. I have the problems here in a worksheet. We're going to be looking at these problems, and we're going to take a look at the inverse function, solving just a few problems in our worksheet. Okay, here we go. Logarithms now. We know about this now. We've studied this. And we can convert between exponential and logarithmic because we're going to be looking at the inverse of exponential functions. We call it the logarithmic. Their first example is an earthquake in this thing called the Richter scale. They realized on the Richter scale, which is how many times worse is one earthquake compared to another. This guy realized that earthquakes can be very tiny and be very bad. But if you measure them and try to assign a number to them, it was really hard unless he used a different type of scale. He called it the Richter scale. And the scale is basically explained this way. When we have an earthquake, it's based on a number, but the number is not, when I have a Richter scale of 2, doesn't mean it's twice as bad. It means it is 10 to the second power times as bad, or 100 times worse. But 2 represents not linearly, but the power of the devastation in the measurement. So the Richter scale was basically based on when I measure earthquakes, it's more useful because they can go from a very tiny amount to a huge amount, like in the millions in some number I measure. It's easier to assign a power of 10 rather than the actual number and have it be 10 times as great or 100 times as great, 1,000 times as great. The Richter scale will be 1 or 1 million. Rather than using lots of digits, they'll say Richter scale 2 means it's 10 times as bad or 100 times as bad. Richter scale 4 means it's 1,000 times as bad. It's just a way of conveniently not dealing with tiny numbers and large numbers with lots, few digits and many digits. Just number the digits. 10 to the 4th, Richter scale of 4. So when we have a Richter scale, if we measure something as 500, we could say that 500 is 10 to what power? 10 to what power gives us 500? Well, what function would I do to that? Well, let's see. I know that 10 squared gives me 100. 10 cubed gives me 1,000. What number x, 10 to what power, would give me 500? Like a graph here. I know that 10 to the 1 power gives me 10. 10 to the second power gives me 100. 10 to the third power gives me 1,000. There's my exponential function. What value gives me 500? Well, we define that function as logarithm. This is a definition that if I want to figure out 10 to some power x gives me y, let's just make up a function. We'll call it logarithm. And we'll say, when we say log base 10 of some number x is equal to y. What I mean is 10 to the y power will give me x. 10, did I say that right? Yeah, I wrote this wrong. 10 to the y gives me x. If I'm trying to figure out what x is. So log to some base, some number x means this number to this power will give me that. So 10 to what number will give me x? Well, let's think of that. Log base 10 of 100 equals y. Question is, 10 to what number will give me 100? Well, I know if I do 10 squared, I get 100. Therefore, y equals 2. Log base 10 of any number means 10 to what number gives me that what's inside of there. So it's just a different way of stating the problem. When when I see this log base b of x, what I'm saying is solve for b to the y equals x. That's the same thing. We're just saying, let's suppose there is a function log. Let's make up this function. When I take the log of some number to some base, I'm trying to figure out b to the y gives me x. B to the y equals x when I see this. It's a handy function because it's the inverse of our exponential. Here's an exponential function. We want to figure out what y is. Just like we did, remember how we did exponential or inverse functions? We exchange x and y. Another way to say this is, let's see, how do I calculate y? Well, I see, take the, what do I do? I have b to the y, I have to figure out x. Well, what do I do? The yth root of b to the y gives me the yth root of x. And what does yth root of b to the y? Gives me b. Now, how do I solve for y? Well, y equals b. Well, I got y messed up in here. What do I do? Well, I define that function. Let's say log base b of x equals y. That's why they define log, because they didn't want to define it this way. Find y, so the yth root of x gives me b. We say, okay, the logarithm function is what we're saying. Logarithm base b of some number will give us y. It's up to us to figure out b to the y, what value of y, when we take b to that power, gives me x. So we're defining the inverse function and we're calling it log. And we have smart math people that have figured out how to do that in a calculator. You don't have to worry about how the calculator does this. All you need to know is what this means. And remember, all that means is log base b of the number x means find the y, so this will be true. Find y, or what y solves that equation. If I know b and x, what is y? If I have b and I have x, give me the y. Okay? So don't get too confused. Just think, whenever I see this, log base b, b to the y will give me x. Let's try to figure out what y is. The calculator will do that for us with the log function. So, can you take the log of a negative number? Well, you're always going to get a positive number when I take b to some power. And b must always be greater than 0. Remember, in our exponential function, a negative number to a fractional power, like a root, gives us imaginary numbers. So b has to be greater than 0. The range is always positive, greater than 0. And b being 1 makes no sense because any number 1 to any power gives us 1. So that doesn't make any sense. So we never have b equals 1. There is no such thing as log base 1. So the input to the logarithm is always positive, but it can give us a range. I can have a negative power, meaning it's 1 over that number to a large exponent. So I can get any real number is my range of the logarithm. So let's look at some problems here and to help understand this logarithm here. A few more minutes to practice this. So back to my problem here, and I'm going to look at a few exercises here to help us understand this. And we're looking at the log example 1. Where's example 1 here? Log base 6 of the square root of 6. Remember what we're thinking about? Putting this in exponential form means this to this power equals that. So exponential form means, remember exponential form is when I see log base b of some number x equals y, it's equivalent to b to the y equals x. So let's plug that in here. 6 to the 1/2 power equals square root of 6, which is, oh yeah, I know that. That's all that is saying. What it is saying here is 3 base b to the 2nd power equals 9. Is that true? Yes, indeed it is. So this is checked. This is correct. All we're doing is putting the same equation in exponential form. That's what they mean when they say put it in exponential form. So, got another problem here to practice this. Is this true? 10 to the 6th power, see, 10 to the 6th power, does it give me that? Equals 1 followed by 6 zeros. Yes, that is true. 5 to the 2nd power, does it equal 25? Yes, it does. That is a true equation. And all we're doing is converting from one form to the other. Remember, all I'm asking, and this time it's written the other way, b to that power, does it give me that? B to the x power equals y. That's what this equation is asking for. So, logarithmic form, let's go the other way. 2 to the 3rd power is equal to 8. So therefore I know that log base 2 of 8 I know is equal to 3. 2 to the 3rd power gives me 8. 5 to the 2nd power gives me 25. Put it in logarithmic form. Log base 5 of 25 equals 2. 5 squared gives me 25. Reverse 25 equals 5 squared. 10 to the negative 4th. Log base 10, that's what I'm taking to the exponent, of 1 over 10,000 equals negative 4th. Because I know 1 over 10,000 is 1 over 10 to the 4th or 10 to the negative 1/4. So log base 10 of 10 to the negative 4th I know is equal to negative 4. So I know then, from this, I know that log of any number 10 to the x power, I know I'm going to get x. And that comes into some way to help solve harder problems. All right, more logarithmic form problems. 3 squared equals 9, put it in logarithmic form. Log base 3, remember whatever I'm doing the power of, that becomes the base of our log. Log base 3 of 9 is equal to 2. 3 to the 2nd power equals 9. I'm going to jump to help you get started on your worksheet, which looks like this. And this is the worksheet that you can complete online, like I'm using this little sketch pad here that I found online at Amazon. Worked pretty well. You can do it with your mouse too, or you could just write it out by hand and show me your notes and just write that out. Log base R of z equals W. I want to put that in exponential form. Remember, all that means is R to the W equals Z. R to the W equals Z. What power of R, when R is taken to the Wth power, I get Z. If I know what Z is, and I know what R is, the question is, what power do I take R to get Z? Typically, I'm looking for what value of W will cause this to be true. And the calculator will do that for me. This one here, the number I'm taking to the power, I use that as my base. Log base 4 of B gives me W. 4 to W gives me B. Log base 4 of B will give me W. And the last one, actually, yeah, we can work on these. Log base 6 of 6 to the 15th. Well, here's my base, here's my value taken to the power, and those two numbers are the same, so therefore I know 6 to y gives me 6 to the 15th. All right? That's what's inside of the parentheses. 6 to the y gives me 6 to the 15th. Well, isn't it clear that y must be 15? When I'm asking to evaluate, they're asking me what value of y, what's the result? So just add to that. When you're evaluating, all that means is put the equals y. Now you want to figure out what y is. I know that 3 to the y equals 27. Well, I know 3 squared gives me 9. 3 cubed gives me 27. Therefore, y equals 3. Therefore, log base 3 of 27 is equal to 3. Log base 5, 125. I know that then 5 to some power y will give me 3125. And in your course, I have given you a helpful little table for this very reason. Let's see if I can find it here. I gave you a table. Find it here. Where did it go? Here it is. Bring this table over here. In section 4, I've given you a helpful table of squares of numbers. As we deal with exponents and logarithms, it's good to go beyond your basic multiplication table, and I start recognizing squares. Some of my favorite squares are the squares of powers of 2, because we use those in computing a lot. But look at here, squares of 5 and powers of 5. I mean, square of 525 to the third is 125. Oh, look at that. 3125 is 5 to the 4th. And so then back to our problem. There you go. Here, 5 to the 4th, 3125. 5 to the y equals 5 to the 4th. Therefore, y equals 4. Last one, and we'll be done. Log base 5 of 5 to the 10th. I'm hoping you're seeing that. 5 5 to what power y gives me 5 to the 10th. Y equals 10. Logarithms, they get more complicated as we do more algebra with them, but we wanted you to just understand logarithms. We will stop here. Check your notes, send me pictures of your notes, and you will get credit for the those assignments. Work on those quizzes, and you will have completed section 4.1, starting easy into logarithms. I will end the recording, and it will appear in the archives. Have a wonderful day.